Hello out there to all my Math 202 students out there in quarantine land, the land of social distancing and compulsive hand washing. When I first heard the term social distancing, I turned to my wife and I said, "The time of the mathematician is here." And then she reminded me that we'd be stuck in our house for 8 weeks with our two small children. So I guess the time of this mathematician isn't here, but in general, the time of mathematician is nigh, and we should all be happy about that. So in this brief video, I just want to give a brief overview of Chapter 7 before we dive into it. So what's the point of Chapter 7 before we actually get to Section 7.1? So just the point of this video is to discuss how Chapter 7 fits into the story of this course. Why are we doing Chapter 7? What is its point? Okay, so to motivate what Chapter 7 is about, think back fondly to your high school algebra class. You solved equations like this. 2x plus 7 equals 3, whatever. You maybe worked your way up to equations like this. But you were solving equations with one unknown, right? One equation, one unknown. And you could do things like factor or square both sides or whatever, right? You dealt with all that in high school algebra. At some point, though, you moved on to something like this. Two equations, two unknowns, right? Or maybe three equations, three unknowns, whatever. So when you do that, when you move to systems of equations, you're now doing something more complicated, I guess, right? You're solving multiple equations at once. And now, with a system like this, your solution consists of both a value for x and for y, so that when you substitute back in to either equation, you get something true. So x equals 14, y equals 2 are solutions. Why is that, right? This pair of data, right? That's the solution. Because, 2 times 14 plus 2 is 30, right? So subbing in 14 for x, 2 for y gives you a true statement here. And then what? 14 minus 4 is 10. Okay, I'm not telling you anything new here, am I? Right? This is very familiar to you. But I just wanted to reestablish this because Chapter 7 for us is about solving systems of differential equations. This is a linear system here, a 2x2 linear system of algebraic equations, right? We're going to now turn our attention to solving systems of differential equations. So thinking about equations like this, but where you have functions whose derivatives show up. That's what Chapter 7 is about. So here is a system of differential equations, okay? There are two equations, notice, right? Similar to this, two equations. There are two unknowns, x1 and x2. Those are both functions of time. So to solve this system, what am I saying? I'm saying that the derivative of function x1 needs to be x1 itself plus x2. What's this x2 we're talking about? Well, there's a condition on x2 also. The derivative of x2 must be 4 times whatever x1 is plus x2. So solving this system means to find functions x1 and x2 such that when you substitute them in to both equations, you get something true. So to solve this system, we have to find all functions x1 and x2, as I said, so that when we substitute in, we get two true statements. So consider these two functions. I'm just pulling these out of a hat, okay? So don't worry about where they came from. Consider this function of time here, e to the 3t plus e to the negative t. Consider this other function, x2, twice e to the 3t minus 2 e to the negative t. Notice the x1 prime, is this, right? 3 e to the 3t minus e to the negative t. The chain rule just pops those coefficients down, right? Notice x1 plus x2. If you were to just add those two functions together, here's x1, here's x2, right? When you do x1 plus x2 and you simplify, you get what? 3e to the 3t and then minus e to the negative t. Okay, so x1 prime is that, x1 plus x2 is that, and then you can complete the chain here. They equal each other. So what do you know? You substitute in x1 and x2 into this equation here, and you write a big check mark. That's true. Okay, similarly, let's check if x2 prime equals 4x1 plus x2. x2 prime is 6 e to the 3t plus 2 e to the negative t. Again, chain rule just popping coefficients down. Notice 4x1 plus x2 is this stuff here. this highlighted stuff. And if you simplify that highlighted stuff, you will get 6e to the 3t plus 2e to the negative t. Okay, so this x1 combined with this x2, that is a solution to this system. So finding solutions, like what does it mean to be a solution? It means the same thing it meant back in Algebra 2. It's just now we're talking about functions and their derivatives. We're not just talking about numbers whose linear sum adds to 14 or whatever. That's the idea of a system of DEs. That's what it means to be a solution of such a system. So in Chapter 7, we will focus on solving linear systems of DEs. So in this example I just did, I just pulled this function out of a hat as with this one, right? Because this should come as no surprise to you. I know how to solve this, right? So I can get any solutions I feel like. Anyway, so the question moving forward is, how do you know this? How do you get these two pieces of information? And is this it? So back in this Algebra 2 example, wherever it was, right? There was one solution, 14, 2, right? Only one solution. Is that the case here? Is this choice of x1 combined with this choice of x2? Is that it? Or are there more? Chapter 7 answers questions like that. We're going to study systems like this. These are called linear systems of DEs. 2 by 2 here just means two equations, two unknowns. You can have a 3 by 3 or 4 by 4, and we will discuss those. But that's what Chapter 7 focuses on. Linear systems like this with constant coefficients here, right? So constant A, constant B, and so on. So in this example we just did, this is linear. There's a coefficient 1, 4, 1. So Chapter 7 just analyzes those sorts of things. After Chapter 7, we will spend the rest of the semester looking at nonlinear systems of differential equations. Even though these subsequent systems are nonlinear, our linear systems will be of use for that material. Now this is nice, okay, so watch this. In much the same way that tangent lines, which are of course linear objects, right, can be used to understand much more complicated graphs like you did in Calc 1. Right, so in Calc 1, why do you spend so much time obsessing over tangent lines? The reason is because locally they're a good approximation of basically any graph that's curved and whose derivative exists. So you can sort of understand a much more complicated graph than a line by just zooming in and looking at these little linear pieces. It turns out that these linear systems here can act in the same way for nonlinear systems of DEs, and we will see that in Chapter 9, and it's super nice. Okay, let me just finish this overview by asking this question. Why would you care about solving systems of DEs? Why bother thinking about this kind of thing? The answer is that, well, in general, if time is your independent variable, there might be multiple things that depend on time, So maybe in this system, x1 represents the number of people susceptible to coronavirus at time t. x2 represents the number of people infected with it. If you could solve this system, then you will be able to make predictions about what happens to those two populations over time. Does the number of infected people approach 100% of the population or not? Whatever. Does the number of susceptible people, can that stabilize, at above half the population? Just whatever. Any question like that, right? If you have populations that you are interested in and you can write down a system of DEs that models that, then solving the DE would tell you what you want to know about those populations. Okay, so basically the rest of the semester past Chapter 7 is just writing down systems of differential equations that model things you might care about. Those things are epidemic spreads, epidemic models, and ecological models. So things like predator-prey interactions or competing species interactions. So Chapter 7 just sets the trajectory for the rest of the course. Systems of differential equations.